Day 133 notes pre-calculus. Today we're going to work a little bit further through section 6.4 from the textbook, and we're going to solve trigonometric equations on an interval. Now, as we mentioned yesterday in the video, in order to avoid domain errors, we must only consider trigonometric functions on the following domains. For our sine function, for example, our sine function should only be evaluated where the theta angle measure is between negative pi over 2 and positive pi over 2, or between negative 90 degrees and positive 90 degrees inclusive. We're allowed to use negative 90 degrees, we're allowed to use positive 90 degrees. We're allowed to use negative pi over 2, and we're allowed to use pi over 2. Now, if you think back to our unit circle, this is what you might see. Remember that the sine of theta is simply equal to the y value of the coordinate inside the unit circle. And if we choose only theta values to exist between negative pi over 2 and positive pi over 2, that would be any of the angle measures in this region here, that's what's going to produce for us any value in our range between negative 1 and positive 1. Similarly, the cosine of theta, cosine of any angle measure, would be equal to the x values of our coordinates on the unit circle. And in order to achieve any value between negative 1 and 1, we can use any theta measurement, any angle measurement in this region here, anywhere between 0 radians and pi radians, or between 0 and 180 degrees. So that's this example here. Cosine of theta will be calculated as long as our theta angle measurement is between 0 and pi in terms of radians, or between 0 degrees and 180 degrees. Now, please remember that tangent of theta is calculated by dividing our y value coordinate divided by the x value coordinate, and we can use any theta angle measurement between negative pi over 2 and positive pi over 2. If we go back to our unit circle and consider what these coordinates might be, you'll see that any of these divisions can be completed and it would return a result for our tangent calculation, with the exception of the points at the very top or the bottom of our unit circle. For example, tangent of 90 degrees cannot be calculated because the tangent of 90 degrees, or tangent of pi over 2, is exactly equal to this y value divided by this x value. 1 divided by 0 does not have a solution. That's undefined. Same thing down here. If negative 1 is divided by 0, that's undefined as well. We cannot find a solution for that point. But if we were to evaluate the point very, very close to that, as long as the x value is not 0, we can calculate the tangent result. And upon further investigation, any point in this range here on our unit circle will calculate an independent result and a unique result without repetition. Therefore, when we calculate tangent of theta, we need only to look at theta values between negative pi over 2 and positive pi over 2. So if we were to look at that in our measurement in degrees, we're allowed to use any value from negative 90 degrees up to 90 degrees, as long as we don't include 90 degrees or negative 90. We cannot include those values, otherwise our result would be undefined. So let's take a look at number 6, or example number 6 from 6.4 then. The question tells us to find all angles theta between 0 degrees and 180 degrees. Now, since the problem indicates that we're working in degrees, we want to make sure that our calculator is set in degrees, especially since we're going to be working with the sine and cosine ratio. If we were doing work without sine or cosine or tangent, if we didn't have any of the trig ratios to utilize, then it wouldn't make a difference whether we're in radian mode or degree mode. But since we are about to calculate a sine and cosine measurement, and our result needs to be in degrees, then our calculator does need to be set to degrees. Before we go to the calculator, let's think about the math that's necessary to solve this. If my objective here is to solve for theta, or in other words, get theta by itself, then what I'm going to do is apply an inverse operation to eliminate this sine from both sides. And that inverse operation is simply sine inverse applied to both sides of the equation, or arc sine, as the textbook sometimes refers to it. Therefore, theta would be equal to arc sine of 0.4. For part B, we're going to rely on the inverse of cosine, which is sometimes called arc cosine. Therefore, theta would be equal to arc cosine of 0.4 as well. Now that we have theta isolated, we can go to our calculator. So I'll switch over to the calculator here, and I'm also going to close this window. I'm not going to save the document, and I'll adjust the settings from here. It's important to go to our document settings, and this time we want to verify that we're set up in degrees. The tricky thing about this calculator is that rather than selecting the OK option that sometimes is present here, we want to make sure that we select the Make Default option and press OK to that. Now when we create a new calculator document, all of the work completed in here will be completed in degree mode. Our first example asked us to calculate the sine inverse of 0.4. So we have sine inverse of 0.4, and our end result is 23.5782. So theta can be equal to 23.5782. Now, that's just one of our theta measurements that has 23.5782 degrees to it. There might be more between 0 and 180. We'll revisit that in just a second. Let's take a look at the result for cosine. Cosine inverse, evaluated at 0.4, returns a result of 66.4218. Theta is equal to 66.4218. Now again, that's one solution. There might be more between 0 and 180 degrees. Remember what this is telling us. What we found is that sine of some angle measure has to equal 0.4. Sine of some angle measure is the x value of a coordinate. Now sine can be calculated between negative pi over 2 and positive pi over 2 without reproducing a range result, but what we're looking for here is any angle measure between 0 and 180 degrees. So we're giving permission for repeated range results to occur. So let's go ahead and see what we get. I'm going to draw this unit circle just a little bit larger. And what we have to remind ourselves is that the sine value is the y value of a coordinate on the unit circle. Now I'm just going to create a quick sketch here. This angle measure theta might have a y value of 0.4. But that's not the only one between 0 and 180 degrees that has a y value of 0.4. If I look to the left in the second quadrant, there would be another angle measured out to here that also has a y value coordinate of 0.4. Interestingly enough, this angle measure here, when measured from the positive x-axis to this point, is the supplement to this angle measure. Those two will add up to equal 180 degrees. So for my second theta measurement, I might even label these as 1 and 2. The second theta measurement would be 180 degrees minus the 23.5782 degrees that we found in the first example. So theta 2 would be equal to 180 minus 23.5782. So that comes out to 156.4218. 156.4218 degrees. Those are the two solutions that have a sine value of 0.4 between 0 degrees and 180 degrees. Similarly, on the right-hand side, we would look for any additional theta angle measurements that have an x value of 0.4 based on their degree. So if I sketch a quick unit circle, that's not my best, but if we sketch a quick one here, we see that this point might have the x value of 0.4. Now, if we're only looking for cosine of theta equal to 0.4 in the range from 0 degrees to 180 degrees, I don't think there is another angle measure that would have the same x value of that coordinate. The only other x value with that coordinate would have been down here. Now this drawing isn't very accurate, so it might not look that way, but a point down here would have the same x value as this first example. But there are no other points in this range between 0 and 180 degrees that has the same x value. So we'll have to leave this as the only answer to part B. Let's take a look at a couple other examples. We're again looking for any angles theta between 0 and 180 degrees that satisfy this equation. So because sine of theta is equal to 1/2, then sine inverse of 1/2 is going to be equal to theta. And over here, sine inverse of root 3 over 2 is equal to theta. Now I should know these answers. Which position in our unit circle has a y value equal to 1/2? Well, the only locations of a y value equal to half exist here and here. Oops, I need to be careful. The y value of positive 1/2 are those two locations. And according to the unit circle, that would have been 30 degrees and 150 degrees. Since both of those exist between 0 and 180, then I would select both of them as answers. So theta 1 I might call 30 degrees, and theta 2 I could call 150 degrees. No calculator necessary, since this was a value that's commonly found in our unit circle. Similarly, for this next example over here, if I draw a quick unit circle, I'm looking for any y value that's equal to the square root of 3 over 2. So that would be a position here and here. And this angle measure, this first angle measure, would be 60 degrees. The next one would be 120 degrees. Since both of those exist between 0 and 180, then I would say that both theta 1, which is equal to 60 degrees, and theta 2, which is equal to 120 degrees, are acceptable solutions to problem number 22. Again, you can verify that work by looking at your unit circle. Here's our 60-degree angle with sine of theta equal to square root 3 over 2. Here's our 120-degree angle with sine of theta equal to square root 3 over 2. Now to finish out this video, I do want to talk about composition of functions. In calculus, we often compose functions, which means to place a function inside of another function. And in order, or the reason why we do this, we need to find exact values of these functions whenever possible. Let me say that again. We need to do this because it helps us to simplify more complicated equations. It helps us with our algebraic work within a calculus problem. So whenever we do utilize composition of functions, we need to find exact values whenever possible. So here's the approach that I would most likely use for a problem like this. If I need to find cosine of sine inverse of 3/5, I'm first going to start with this innermost function. And maybe off to the side I'll remind myself that sine inverse, or arcsine of 3/5, must be equal to some number. Now in this case, since we're dealing with an inverse, this is going to be equal to some angle measure, theta. Now to say that sine inverse of 3/5 is equal to theta, that would be the exact same as saying that sine of theta is equal to 3/5. So a regular sine of theta is equal to 3/5 is the exact same. These two are equivalent statements of arc sine of 3/5 is equal to theta. Those two mean the same thing. Now this is telling us that sine of some angle measure is equal to 3/5. Well, you can't forget that when we're dealing with sine, we're dealing with an opposite over an hypotenuse. Opposite over hypotenuse. So let's sketch a quick triangle here. If I have some angle measure theta, and I know that it's equal to 3/5, that means that the side lengths are 3 and 5. Well, it wouldn't take much for us to find this missing side length here to be 4. This is a 3, 4, 5 triangle. If it wasn't that obvious, then we'd employ the Pythagorean equation and consider this A, B, and C. A squared plus B squared equals C squared. We can use that to find this missing side. Now, since we spent the time to find this missing side length, we don't really have to identify the actual theta value to make this triangle. What I mean is that since arc sine of 3/5 is equal to some theta measurement, that's just like us saying cosine of some theta measurement can be found in the same manner. Well, cosine of that theta, the theta that satisfied this statement just a moment ago, is the exact same theta that we need to evaluate cosine for. Well, cosine based on that theta is simply equal to its adjacent side divided by the hypotenuse. And since we found our adjacent side, we can show that cosine of that theta is equal to 4/5. Therefore, the composition of functions cosine of arc sine of 3/5 is simply equal to 4/5. In a similar fashion, we can complete example number 8 as well. Let's take this first one for example. We need to write sine of arc cosine of x as an algebraic expression in terms of x. So let's start off by saying this. Cosine inverse or arc cosine of x must be equal to some angle measure theta. That would be the same as saying that cosine of theta is equal to some unknown value x. Now if we sketch a right triangle with an unknown angle measure theta, well, cosine of theta has to equal x. So cosine, I'm going to call the adjacent side over the hypotenuse. Let's just choose an easy hypotenuse of 1. That would make our adjacent side down here equal to x. Cosine of theta is equal to x over 1. Now to finish out this calculation, to find out what sine of cosine inverse of x is, we simply need to find the final missing side over here. So I know that using the Pythagorean equation that a squared plus b squared has to equal c squared. Well, let's set x equal to a, so this is x squared plus b squared equals 1 squared, our hypotenuse squared. In order to solve for b, I would subtract x squared from both sides. 1 squared is 1, minus x squared would have b by itself. When we square root both sides, b would then be equal to the square root of 1 minus x squared. Therefore, we can say that sine of cosine inverse of x is truly equal to sine of some unknown theta, which we actually didn't even need to calculate, sine of some theta in such a way that cosine of theta was equal to x, and the theta required to make cosine of theta equal to x would be the same theta required oops, not to write it this way, it would be the same theta required to make sine of theta equal to the square root of 1 minus x squared. So we can go with that as our final answer. That may be a bit tricky for some of you if you haven't seen this sort of algebraic work with our trig functions before, but I encourage you to try the second half of this example on your own. Simplify this statement by using the exact same techniques that we practiced in the last two examples and check your work. This example can be found on page 440. Come to class having tried that on your own, and I'd be happy to help you with any questions along the way.